Hello, everyone. Welcome back. I hope you had a good weekend last time, and then we're ready to go into the next weekend. We had 4 days to catch up on any of the materials. So the YouTube video is out there. The link is posted here. In addition, I have added a bunch of material for today. So if you go to the folder that is shared with you, SIGGRAPH Now July webinar series, and there's a bunch of folders in here. Also, here is a PDF for slides from the last lecture. And today's material will be under the 15 July course files. There's a bunch of files here that we will use them today. So we'll pick up from where we finished last time. So again, this is me. Make sure you're in the right lecture. Reading the SIGGRAPH anti-harassment policy again. Exercise consideration and respect in your speech and actions. Refrain from demeaning, discriminatory, or harassing behavior. Be mindful of your surroundings and your fellow participants. And if you see anything, please alert any of the moderators or me, and we'll follow up on that. So again, this webinar series is brought to you by SIGGRAPH University. With many thanks to all the organizers and the SIGGRAPH chair, people at Smith Buckland, comics by Mia Tang, and then thanks to you for being here and taking lessons about this. So this is the lecture 2. And we are going to follow this rough guideline on the course material, different materials for different days. And you already know this that I talked about. Just to give you an idea, last time we talked about a bunch of different things. And then if there are any more questions, please feel free to post them in the chat. And we also kind of ran out of time to talk about some classification and the theory around all those. So we will cover that. So today we'll also do classification using an example for flower types. We'll cover a bunch of different kinds of neural networks and then go into some theory as well. So just to recap, like a lot of questions around network size and depth last time. Like how do we choose what number of nodes to use or in each layer, or how many layers to have? So, and I said, yeah, it's like an art form. There are hyperparameters to your network. You can change them and adjust them as you go. The main idea that I want you to take away is that in a layer, as you feed in all your inputs, you are going to transform them. First of all, you're going to have weights at each node that you're going to multiply by the input. And then you're going to do some activation function at each node that will introduce some nonlinearity, either using sigmoid or the ReLU. And so this operation is happening at each step. And because each node is connected to every other node in the next layer, you are basically sharing these weights in a way where you get these attributes shared. So as you go from layer to layer, there's a lot of mixing goes on of the weights and the attributes. And all together, you end up with this very long linear equation that is multiplying this weights by the input and then doing this activation function on top of it and then summing it up. So you go do that all the way through. You end up with a very long equation that approximates essentially what your data has been input. So think of it as like, as you make more nodes or more layers, you're introducing more computation in there, but it also helps to kind of distribute the load. So like if you have only like 4 weights and you have 50 inputs, all those weights that are like fewer in number, they'll have a hard time understanding your data, because now all your data has to be kind of understood by just a few nodes. So imagine that spreading that out, like you have larger number of weights in your network, then each of those weights can understand a specific feature and then be a little bit more specialized. So that way, when you end up with a linear equation, you different weights kind of pull the network in different directions and kind of give you a deeper understanding of your data. So that's like one way to think of it. This is just data and weights and inputs. Another way to think of it is like more in terms of data transformation. So each layer essentially takes your data and moves it into some space that is multidimensional based on the number of nodes you have. So imagine like you're doing some kind of a transformation to your input data that puts it in some weird multidimensional space. So this is like a transform from one space to another. You got your data and you passed it to the first layer. It ended up in some multidimensional space. And you do this again and you have another multidimensional space. So the hope is that like when you do things like classification, that you find a space that can separate this data so that the data that is similar to each other ends up being closer to each other, and then data that is different is clustered differently. So that kind of gives you a better sense of like how you can partition this data. Again, these higher dimension spaces, they are like very hard to visualize, and they could be like 100-dimensional spaces. But just realize that every layer basically transform your data into some other higher dimensional space. And we'll get more into that when we talk about distributions. Another question was around bias and variance. So bias and variance basically are things that you want to avoid, right? So the bias was when you had your learning is not is very coarse, so you haven't learned enough. So this is like mapping a straight line to data that is spread out in more of a curved form. And then variance is the opposite of it, where you have learned too much. So you have memorized the data where your curve is an exact fit almost to the data. So both are bad. So in bias, you don't understand, you don't have a good model essentially. And with variance, you have overtrained or overfitted your data. So all error that comes from from training is a mix of either bias or variance or some irreducible data. So the irreducible data error, you cannot fix it. It is something like outliers that pop in where you made a copying mistake. So that kind of error is unavoidable, and it's not possible to kind of reduce that fully. But bias and variance you can try to fix as much as possible, and you have a push and pull between bias and variance. Again, it's just a fancy name for underfitting and overfitting. And some of you had asked about like where to learn more. So there are conferences, and they're very popular conferences, hundreds of papers published each year in each of these. And the state of the art moves pretty fast in this field. So you can either read these conference proceedings, or a lot of people now are putting out preprint on the web. You can find the PDFs. And also, a lot of people now put out their models, either PyTorch or implementations in some other packages. So you can always like download those and run those and try to learn from those. Again, the research moves at a pretty fast pace, so it's hard to keep up sometimes. For the basic understanding of different things, I think these three are my favorite books. First one introduces you to more of the math and the statistics behind everything. And deep learning book is kind of like the deep learning Bible. You have all the things you need in there. It skips on some of the math, but it has very good theory in general, and a lot of different algorithms are there. Deep learning by Francione, he is the author of Keras that we are using. His book is very good practical book, and it's a great read. So we just came up with the second edition just last year. So all those three books, I think if you read from them, practice them, and then of course this lecture, you can use that to augment your learning. All right, so instead of going to Autoencoder, let's finish up the last week's lecture, which was around classification. So we did we did a simple regression for housing prices. And any questions on the regression part of the housing price? Did anyone try to change the hyperparameters? Did you learn anything from changing things? Okay, so you can type up your answer and we'll read them. And hopefully you did. So next we move into something called classification. So we did regression earlier, and regression, we had basically one output and we had the ground truth and we tried to match that. So classification is a different kind of problem where we try to basically divide our data into different classes. So the simplest example is a binary classification where you have only two choices, or really there's only like true or false. So if you have pictures of cats and dogs and you want to classify them whether they are cats or dogs, and so that's an example of a classification. So we'll use this flower project as an example and learn about how to do classification, again, with the similar kind of neural network that we use for regression, but this time we're going to do classification instead. Just to give you some background on this data has measurements around the iris flowers, and there are species represented there, which for which the data has been measured. And there are 4 parts to the data. One is the petal width, the second is the petal length, and then the width and the length for the sepal. The sepal for a flower is usually green. It holds the flower when the flower is young, and then as the flower blooms, they kind of hang to the side, these green things. But in the iris flower, they are also violet in color. So they're larger than the flower petals, as you can see. So we'll look at this data and then see, like, within the multiple species that have been given to us, can we just deduce from the data which species a particular flower might belong to? So this is the data that will be given to us. Again, it's kind of messy in the way when we read it, but you can see this is the number of data points, 120. We have 4 features in there, the with 2 widths and the 2 heights, and there are 3 species, and they are listed by their string names. 4 data points as an example to show you: width and height, length and width, and which species it belongs to. So this would be 0, 1, and 2. So it's a little bit cryptic, but once you kind of read through it, you can see what the data means. So as the first step, again, we are going to look at this data and do the usual splitting for the training, normalize the training data, and then look at how to build a network for classification. So let's open the file classification, or the flower classification file, and we'll go over that right now. Let me find that. So this would be this one. So let me start by clearing all out those. So again, as usual, we import some libraries to help us out, same as before. And this particular data comes to us from somewhere from Google TensorFlow, and it's called iris training CSV for comma separated values. And we're just going to go ahead and read that. While virtual machine connects through. So, and we say, okay, print the first 12 data items. So there it is. Same thing that I showed you on the spreadsheet here. And these are the pictures of these 3 species that I found on the web, and this is what they look like. So again, because this is so cryptic, we're going to kind of put this data nicely together so we can make sense of it. So I'm going to give them column names. So length, width of the sepal, and the length, width of the petal. And then the last column is the species. And then we'll have the class names as what they are. So I'm just going to assign this to our data, pandas data, and then let's see what it looks like. So now it's a little bit more descriptive of what they are. We know how many data points, 120, and there's their average values and standard deviation. So let's do a pair plot now of, this is a small amount of data, 120. So we should be able to plot them all. All right, so this is again a pair plot from Seaborn, which we saw last time as well. It plots every feature against all the other features, and when plotting against itself, it just gives you a histogram of the distribution. So right away, you can see there's like a lot of linear relationships here, and you can see that these things are like straight lines because they are they're not floating point numbers, because they are real numbers or like integers 0, 1, or 2. And that's why the data looks like this. So that's the species. And so this looks like there's some linear relationship here, but all this looks a little bit jumbled up. So we can do more. We can color code these things. So let's do the same thing, but this time use the color of the species to index into a color for these dots. So let's wait for a few seconds. There you go. So now we have much more insight into this data just because we color the different points. So species 0 is this color, species 2 is the darkest. So already you can see that this particular diagram here, I don't know if you can see my mouse. You can already see that all the species 0 is on the left, and species 2 and 3, they are the ones that are intermixed, but species 1 is pretty clear which one it is. That's the one that has small petal length, right? The petal length is small, and so it's like you don't even need machine learning for that. You can already classify this. So like anything that has a petal length of less than 2 is species 0. So their classification done, no need for machine learning. Somewhere here, things get a little complicated. Like you can still do some things where, okay, if you just draw a vertical line here, you can separate most of the data, but then there are this intermingled data that you can't separate. So you'll still get a pretty good classification. You'll get weird errors in this area. So, but you can still just do based on a visual inspection of the data, you can make pretty good choices already. So, but because this is a toy data and it's designed for learning, so we're just going to play along and then use neural networks to train this and learn how to classify. Any questions on that data itself? All right, so we're going to do the usual. We're going to split into testing and training, 80% of the data for training, 20% for testing, and separate out the Y column, that is our ground truth. Same thing for testing. And then let's see what it looks like. Something. It's pretty good. So we got 80% of the data for training and 20%, 24 data points for testing. So this is where we're going to build our neural network. So if you look at this, this is actually exactly like last time, what we did for regression, because we haven't changed anything. It's a dense network of 32 nodes in 2 layers, and then output. So the output is the one that is different. So we have 3 outputs now. So in last time we had 1 value to output, which was the median home value. This time we have 3 values to output. which species it is. So what we want to be able to do is these three outputs, one of them will be one at a time. So whichever is one or true, we say that is the species. In reality, we'll have three probabilities. One would be, say, 10%, 10%, and 80%. And whatever has the maximum probability, we'll choose that as the answer. So let's build that model. The second difference that you'll notice here is the loss. So we have specified a loss here, something called a sparse categorical cross entropy. It's a mouthful. We'll go through that later in the class to kind of go into what that is exactly. But for the purpose of this exercise, just assume that it's a loss that will give you these probabilities. So this is our model. Again, not too different. And we'll plot this model, same as last time. So we can train this. So we haven't trained that yet, so we don't want to predict. So let's train this. So again, same process for training. We choose a smaller batch size because our data is only 120 data points. So we don't want to pick too large a batch size because then otherwise it becomes meaningless. So we'll train for 10 epochs. We'll have some validation split, and let's do that. So this should train pretty quickly. There you go. So we have our loss going down, which is good, accuracy going up, which is good. It's not so great, but it's okay for testing our network and training. Like, okay, this works. Let's plot the losses. So loss is going down, which is good. So now, as I said, this thing gives you the probabilities. So what you do, actually what it gives you is something closer to probabilities, but just called a log likelihood. We'll also get into that, what it means. And we convert that to probabilities by running a function called Softmax. And Softmax is just a normalization process. It's a exponential normalization, which brings everything into the range of 0 to 1, and it pushes things that are kind of closer or to 0 or close to 1 in either direction. So you have this nice kind of conversion from any kind of range to a range of 0 to 1, because we want our probabilities to sum up to 0. So the softmax function is used very often to kind of convert any kind of range of numbers into a range that is from 0 to 1. So now what we do is we take the max of those probabilities. So again, you got log likelihoods, you converted them to probabilities, and from the probabilities, you find out which one is the maximum to get the max out of those three values. And whichever is that class, we'll say, okay, this is it. So right now, this is the predicted classes and the actuals. We printed that, and you can see like some of these are wrong, but that's the accuracy of our model. So it's hard, again, like if you had a lot of data points, it would be hard for us to kind of keep comparing these values. And last time for regression, I talked about how you can draw a diagonal line of predicted versus actual values, and ideally they would all fall on a diagonal if your prediction is good. And another way to test that was to see if the errors themselves are normally distributed. For classification, it's hard to do that, right? So we need to find another way to do that, and for that we need a little bit more theory. So we did that, and we talked about this log likelihood. So you can imagine that our network will return values something like this, and they could be in any range because they're just linear equations, weight multiplies, and what we do is the softmax function. The softmax function, as I said, is just an exponential normalization. In any kind of normalization, you divide the value by the sum of the rest of the values, and that kind of puts it in that range. So this exponential normalization or softmax will convert that into range 0 to 1, which is great for probability. So this gets converted into these. And then from these three, we can say, okay, this is probably the most likely category. So if it's A, B, and C, then B is the most likely category. So that's the basic math behind it. And then we trained and tested it. So as I said, like we have a problem because now we can't see the results in a graphical form. Like, what does it mean for the prediction to be right or wrong? Because if you plot them on a diagonal, they will all get plotted on the same place, because if the category matches, then they're here. If it doesn't match, it's somewhere here. So it doesn't, because all the points are on top of each other. We don't know how many were correct or how many were wrong. We just get this kind of graph where we can't learn from that. So to get around this, I'm going to digress a little bit and then talk a little bit about how to evaluate classification. So we go into a little bit of an exercise in probability. So imagine like there is a population of 10,000 people, and there is a disease. This is very timely. It's a disease that is has 2% incidence, and then we have a test for it, which is 95% accurate. So if you take this population of 10,000 where 2% are likely to have the disease, and 9,800 out of the 10,000 don't have the disease usually, and then you give them all this test, which is 95% accurate, and then you will have about 190 people testing positive for the disease, or then 5% testing like they don't have the disease, and same thing with the rest of the population. So here you see the dilemma where you have a large percentage of people. So by the way, anyway, like we can label these. So positive, negative, negative, positive test, right? So you can see that the 490 people that got tested positive probably don't have that disease. So the test, although it's 5% is 95% accurate, if you look at like how likely you are to have the disease if you test it, it is pretty low actually. So it's just the 190 over sum of 190 over 490. So it's about what, 25%. So it's like 25% chance of having the disease for a test that is 95% accurate. So that explains like the reason why you want to give importance to the base rate as well, because the original population, the incidence of the disease is fairly low. So the test has to be much more accurate for you to kind of have a higher percentage, so that you don't you want to reduce this number, you want to increase this number. So there are names for these. So you had positive, negative test. Anybody know what this particular thing can be called? You might have heard of phrases like false positive. So this is false positive. This is true positive. So that's the negatives are the counterparts to those. So those things, we can label them as such. So this is a great way then for us to test the classification, because each classification can go wrong in two ways. It can either be that it belongs to some class, but it was predicted as not belonging to that class. And it can go wrong in the other way, where some other thing that belongs to some other class was predicted to belong to our class. So again, so you want to avoid both of those. So there are two kinds of errors. So that gives us a matrix like this. This thing is called a confusion matrix. And this gives you a very good idea to evaluate like how many things are in each of those boxes. So you take all these samples and evaluate, but okay, if the actual value is positive and the predicted result is positive, then it's a true positive and you put a number there. So you can change this positive, negative to actually be true or false, doesn't matter. So we can do the same thing with our classification data. We can plot a matrix like that, where this part would be the species, whether they were predicted correct or not, and we can have how many things were predicted correct or not. So let's do that for our data. So this thing, we are going to generate a confusion matrix from TensorFlow using our data, and then we're going to use Seaborn to plot it as a heat map of different shades of blue. So already we can see, and this we suspected already, right? Just by looking at the data, we knew that the species 0 is the easiest to classify. So nothing has gone wrong there. It's perfect. There is no item in species 2, so it probably got confused here. So between these two, so you have species 1 and species 2. So that's where the confusion lies. I think this particular, the 0, species 0, 10 were predicted and 10 were tested, and it's all good. So you want ideally everything in the diagonal to be full and nothing in any other box. So if you have anything in any other box, which means that that's an error of either a true positive or either a false positive or a false negative. So let's see if we can reduce this error. So any suggestions on how we can reduce this error? Yes, no? Wait, let me minimize this. I don't need to see myself. Okay, so the easiest way to do it is to just train more. So we can do two things here. We can add another layer, or we can train for longer. So let's try train for longer first. So where was it? Here. Let's train for twice as long. So the good thing about Colab is that it will remember where the weights were, because we're not resetting anything, we're just training again. So it will start from where it left off. So you can already see that if you train for longer, the loss decreases pretty quickly, and the accuracy increases. Validation loss is also decreased. The validation accuracy has also increased. So let's plot this again. That's pretty good. And evaluate the model. And now let's try to predict. So pretty much one error around. So if you plot it now, two errors actually. So this is, we just tested part of the data here, but in the rest of the data, so there are two errors. So we've done a little bit better, which is good. Again, because this is just a small data set, the danger here is that if you train more, you are going to overtrain it, and you are essentially going to memorize it, where the accuracy is 1, but if we get more data from somewhere, it may not generalize well. So let's show you what the overtraining looks like. That's good. Still the same. So that didn't change. So what other thing we can try is now is to just increase the network. And this will reset everything. Name conflict. So as we know, the number of parameters will increase. things will take a little longer. Predict. So made it a little bit better, even more. So you can keep doing this and then playing with it, and you'll finally come up with a solution that you're happy with, and that's your final model. Any questions around? Let me get back to the chat, because when I'm presenting, I don't see the chat. So I'm going to. Okay, I need to bring up this Q&A thing. Hold on. Right. So the question's around like which optimizer to use, RMS, prop versus Atom. So it's, again, all these things are there to kind of accelerate your optimizer. Shouldn't make a big difference, but then I think as you get into more of the very granular adjustments for networks that have been running that take a very long time to run, you want to kind of try one versus the other and see. So there are like the bigger hyperparameters, the network size and the network depth. Those make the biggest difference. And then the rest of it is about optimizing and running your network as quickly as possible. So those make smaller differences, but those smaller differences can mean a lot to people who are kind of training a large amount of data for very small little change. So that was a great answer to like how we train better is by training more epochs, more layers, lowering training rate. So that's all good. So another question about like how do we choose? So I think this is going to be like the ongoing question. Like how do we choose? So because there's no real answer to like how do you choose whether to make your network deeper or harder. So these are experimentations that you can try. You can even write scripts that that kind of take in a range of values for number of nodes or the depth of the network, or training or learning rate, and then run them all as a big combination of different values, and then pick the one that works the best for you. So there are even ways in a lot of the toolkits to kind of set a learning rate, where the learning rate initially for say first 50 epochs is large, but then as time goes on, it can automatically start reducing the learning rate. So there are a lot of methods to kind of do a trade-off between training it faster and training it better, and you will have to choose them. There's some guidelines, but there are no hard and fast rules for those things. Okay, so now let's go back to some of the things we talked about that need a little bit more explaining. So we did the heat map. So let me close this window because now there are too many windows on my screen. So we talked about this cross entropy, and we talked about like, yeah, this generates log likelihood. So what is that? Let's go over that a little bit because it's important sometimes to know what's going on there. So hopefully you've all heard of something called a normal distribution, sometimes called a Gaussian distribution, or in regular parlance, the bell curve. So bell curve basically defines the probability density based on two parameters, which first of them is mean, and second is called the variance. And so a lot of things in life, they are kind of normally distributed. And natural and artificial phenomena, they kind of distribute themselves normally in a way which follows the probabilities described in this particular graph. So the shape is a classic bell curve where there is a peak and then it slopes gently. It never really touches the bottom, which just goes like as an asymptote on the sides. So what it tells you is that on average, the distribution is centered around the mean, and its probability is the highest at the mean, which is the peak. So where you see mu in the center, get the mouse. So this mu is in the center. That is, mu is also the mean of the data. And then if you look at the probability for that, which is, this is the maximum. So, and as you go away from the mean, the probability of the samples being in that distribution keeps falling off, either to the left of the mean or to the right of the mean. So as you go farther away from the mean, they kind of start falling off, where this 3 sigma away from the mean, you have like almost 0% chance of that event happening, but it's still a positive number. It's very unlikely. So if you look at some of the data, like heights of male in the United States, so that follows a normal distribution where the average height is 5'8", and then that is the peak and the mean. Then away from that, like shorter males will be along this, taller males will be along this. There may be a 2-foot person who falls somewhere right here, 4 sigmas away, a 10-foot person who falls here, 4 sigma away on the right side. So as you go farther away, the events become more and more unlikely, though still possible. You may have things that are like 6 sigmas away. If you've heard of the term 6 sigma, that kind of describes the accuracy of the processes. So that's like the rate of error is so minuscule that your process is now certified as a 6 sigma. So that's like a pretty good process if you can certify it as a 6 sigma. So there's some inconsistency between what I'm describing here as a mathematical normal distribution and 6 sigma versus how the process industry describes it, but that's the general idea. So the good thing about this distribution is there is a formula for it, so which is analytical. You can differentiate it, and it is predicated on just the 2 parameters, and the sigma and the mu, and you can calculate these values. So why am I describing all this? Is that you can have different shapes. You can have distributions with high peak, low peak, wider, shorter. So all depends on the mean of the data. So if you are, say, manufacturing some machine part, say just a screw. So your machine manufactures screw, and ever so slightly there'll be variations in the, say you want to manufacture a 1-inch screw exactly. And as the screws come out, because the temperature changes, the difference in the metallurgy process, there may be slight variations. So some screws will be just slightly bigger, some will be slightly smaller. Ideally, if you are a factory manager, you want that curve to be as narrow as possible. You want most of the samples to stick as close to the mean, which should be 1, and then you want that curve to be as narrow as possible. So this, like, different shapes kind of tell you more about the data, the distribution that comes from it. So let's take this further now. This is what we did for linear regression. So we did this mean squared error, which basically came out to be this square of the difference between the actual and the predicted value, and that gave you the error. And then our goal was to minimize the error. So the way we did minimization was to differentiate it and figure it out. So this was good for simple linear things. This is tractable, analytical, that you can differentiate normally. As you get more complex input, things may be hard to differentiate. So what we are doing here actually is trying to find a distribution. So imagine like each of these is a screw that the average height, you want that to be as close to the mean. So we are essentially trying to map the value that you have predicted to be as close. So you don't know the original distribution, but you want to map it to something like, say, a normal distribution for which you're going to maximize this. So now taking a look at this formula for the probability density, which was given by this. So if we, this is for all events, and if you have multiple data points or multiple events, the joint probability would be the product of all the probabilities, right? So if you had 10 data points, you would have 10 of these multiplied together for each data point. So this equation then can transform into this one. Everybody with me? I think it's nothing, just substitution. You're basically multiplying all the input data one by one. This is the product. And now this is what you got, but then this is again hard because how are you going to productify this thing? So what you do is you take log on both sides. So when you take log on both sides, the product becomes a sum. And you get this other term from here, and this thing becomes basically a big summation here. So if you look at this carefully, and then if you further simplify it, you'll get this. So this is your probability of, that's what you want to maximize. And after you further simplify it, you'll get this particular equation. And this looks very familiar. This is exactly the same as the least squares. And because you are minimizing the probability, and here there's a negative number, it basically is this exact same as minimizing this, right? Maximizing probability turns out to be minimizing the least sum square error. So it's both exactly the same. But now we have generalized it to any probability, not just linear, not just data points in 2 dimensions, but this can now be generalized into any dimension. So that's why I think most of the toolkits, then they want to generalize data, and you want to think of like as you learn more and more, you want to think of it in a general problem solving sense. So you can now think of least square minimization as a probability or likelihood maximization. So everybody clear on this? This is a key point, because this is, once this clicks, I think the next part would become much easier. Like you get a better understanding of what is happening. So let me pause here and take some questions. So we had a question about, like, when adding layers for classification, should the number of parameters per layer increase or decrease? Well, the number of parameters is dependent on how many nodes you have in a layer. So as you add more nodes, the number of parameters keep increasing. And the formula that we talked about, or the math that we did last time, was you take the number of things coming in times the number of nodes in the layer plus some number for the bias. And it's up to you. You can increase the size of the network. You don't have to have 32 in each layer. You can have 32, 64. You can do whatever you want, really. So this, like, imagine this is, you're like distributing all the calculations as much as possible. So you have full freedom to do what you want. All right, so I hope it's clear. This oh my God, it's taking up all my window. I'm gonna minimize this again. That least square minimization is the same as maximizing likelihoods, log likelihoods, as they are called sometimes, because the formula turns out to be the same. Now we have generalized this to any kind of distribution, not just linear, and we have generalized this to any kind of dimension as well. So there is another view which comes from information theory due to Claude Shannon. So this is excellent 1948 paper on entropy, which measures how much surprise or uncertainty is conveyed by an event. And this is the formula. I'll just give you the formula without deriving it. It's basically says you sum up all the events that are happening, take their logs, and sum them up, and that gives you a measure of entropy. So if you just kind of look at this formula, you can kind of guess that things that have higher probability, they are actually low information. It's like you want surprise. You want low probability events to happen. So lower probability events will generate higher entropy, and vice versa. So, and there is something else called cross entropy. So if you have two distributions, you can kind of compare them by calculating this entity called cross entropy, where you have usually what we do is we have a actual distribution and a predicted distribution, and you can find, in a way, this measures like the difference or the length between the two probabilities. And this is the formula for measuring that. It comes from the entropy formula. And sorry, just ended the lecture. So just keep in mind, I think those formula for the entropy and cross entropy. And then when we talk more in terms of how the distributions happen, I'll come back to that, and then we'll tie the whole thing together, where the cross entropy and the maximum likelihood and the minimization of the least square error, they're all essentially the same thing. Okay, so now let's do some more concrete example. Next thing we're going to talk about is something called an autoencoder. So this is what we did for our regression. We had a fully connected network, and just everything was connected to everything, and then we had an answer at the end. So we can take shape this network a little bit, where we're going to squish it in the center. So conceptually, think of it like this. So you have input on the left, and that gets squished in the center. Basically, you're taking all your data and then transforming it by layers into some latent space. This latent space is in some other dimensions. And so it's not like your data doesn't look like what it used to look like. So that's why these meerkats here are kind of like in a weird shape. So what we will then attempt to do is try to reconstruct our original input from this latent space. And there's a process that will follow that will reconstruct it. And because we compressed our data in a way, we're not able to fully reconstruct it. There's always going to be some errors. So when you get back your data, it's going to look slightly different, but it's going to be pretty good. So that's the basic idea behind encoders and decoders. So it's a single network that has both. And all it is a normal neural network that is fully connected, just squished in the center. So this is what it looks like. So you take your input, you make some layers, and then you purposefully, in the center layer, you choose a smaller number of nodes, and then you keep expanding it back to the previous one. So now what you can do is you can take the input data, shove it through here, and as you get out the data, you can compare it against the original data. And if it is different, we keep training and distribute the errors, and over time it will start generating your original data. So in this case, our ground truth is the same as the input data, right? Because we're trying to reconstruct the same exact thing. So as a more concrete example, say you had this image of a digit, and this is a classic toy data set that you take an image and you encode it by using the encoder part of the network, so which was essentially the blue and the red dots. And then you get some representation here. And then that you're going to push through a decoder part, which is just the expanding part of the network. And then you get some output that is reconstructed form of the original output. In reality, I think this is all connected because you are comparing with the original, and then you're changing the weights based on that. So let's look at the autoencoder now. We'll make one with the images. So we're kind of like advancing a little bit. We were dealing with numbers before, and now we're going to start dealing with images. Any questions on this? All right. So by now, this should be very familiar. We have some packages to import. We're going to import them. This time, we are going to load a data set. So again, this is no file to load. The TensorFlow already has this data set available. It's called MNIST. It is the handwritten grayscale images, and we are going to load it. So when you get data out of TensorFlow directly, it has a certain format. It has already been kind of prepared in a way for you to be able to easy to train. So once you get that, we kind of break it up into two parts, testing. So this data in particular is designed for classification exercise. So we're not going to do classification on this. We are doing an autoencoder neural network. So we're going to ignore the ground truth that is given to us. So we look at this data. What it represents is 60,000 images. Each image is 28 by 28 grayscale. And that's in the training set, and then 10,000 images in the testing set. And they also provide us with a ground truth, which essentially tells you what number it is. So because these images, you don't know whether it's a 5 or a 4 or a 3 or 1, you get an additional column of Y. So if you were to ever do classification, you can do that also, but we're not using this particular part of the data for this exercise. So let's see what this data looks like. So again, we're going to use plotted. This imshow will show an image. So we're going to take the first 10 data points and plot them, and that's what they look like. They're handwritten digits. Again, they're very small. They're 28 by 28 pixels, so you must almost see each pixel here, and they're grayscale, so you don't need any color information. So now let's build the autoencoder model. So here it is. Input layer is 28 by 28, so that's image. And what we're going to do is we're going to take our image 28 by 28. We're going to flatten it into one large column, and that will be our input data. So imagine how we had features, like we had 4 features in the flower classification. In this case now, our features are 28 times 28 that has been flattened into one single column. So now it's a huge amount of input parameters for a neural network. So we did that, and then we are going to create a dense layer. And then we are going to, so this is, the output layer. We're going to reshape it to, again, go back to an image. So again, all it is doing is you just have essentially one layer here. And that's all it is. So you're taking from 28 times 28, squishing it down to 32, and then expanding it back to 28 by 28. So let's see what this looks like. So already you can see it's a huge number of parameters. So this is in 25,000. So imagine if you had large images. So this is a 28 by 28 image and in grayscale. So if you had a large image, say it was 500 times 500 image, which is not really large. It's like this big. And then you had 3 colors per channel and you had 32 nodes and you add 32 more for bias. Imagine the size of our network. It would be humongous. So that's why you'll find in most cases, in all research papers, most neural networks are trained on very small images because it's so hard to train on such a large amount of data. So you get the model, you can compile it. We're going to use the mean square error loss and try to fit it. So this is the simplest of the network, all squishing it down to 32 and then expanding it back to 784. So while it's doing that, let me explain to you, I'm like showing, because you want to be able to compare images. So I wrote some code here to basically, nothing special here. It's just Matplotlib has weird syntax. So you essentially have subplots. So we're going to index them so we can look at them kind of next to each other, original and decoded. So it looks like training is done. And let's I'm going to run this just so this. So you have original and decoded. So you can see it does a pretty good job. Such is tiny network from kind of compressing it down to 28, from 28 by 28 to 32. That's like a factor of 24. So compression factor of 24, that's like amazing. But you have lost some because these images, they kind of look alike, but there's, you can clearly see there is loss, especially in this 9. You can see that some bits have gone soft here. And this 9, there is a small line in between the circle that is not visible anymore. So, so that's the drawback of it. You'll have some loss that is not recoverable. But given the kind of compression you get, it's an amazing thing. So we can use this for many other things. So this is one way to reconstruct it. Imagine if you had like old pictures that, and then you wanted to clean them up. So you would have like, if you had some color corrected images that you can train as the ground truth, then you can start kind of cleaning up your images. So there's like many applications of this. In general, these kinds of networks are called denoising networks. And then you don't even have to use autoencoder for those purposes, but this is like a building block for you to understand more why we might use such a thing. So, in the first lecture, I said that a simple network can solve pretty much any equation or approximate any equation or any data set, but at the cost of a lot of data, a lot of memory. So a lot of effort has gone into research, into kind of finding ways to kind of reduce that. How can we use a less dense network? How can we use a different formulation of the model so that we don't have to train for that long, or we don't have to have as many nodes or parameters to use. So autoencoder is one way to do that, and we will cover something else that is called CNN, or a convolutional neural network. Before we get to that, like I wanted to give you some examples of like the kinds of things you can do. So this is something as a more practical application. So when you do ray tracing, you have this inherent limitation where the noise doesn't converge unless you let it run for 5-6 days. So one way to speed up rendering is to kind of train these pairs. You have some examples that you can render fully for a long time, and you have others that are noisy, and you can train them for a long time, and then you can come up with a neural network that will now be able to denoise images that it has not seen before. So it's one of the major practical implications in the film industry, games, is this denoising, and that's pretty much everywhere now. So one other thing is that this is all vision kind of based, right? So you are looking at the image. You're not looking at this number 7 or 10. You're looking at this image. So the computer doesn't understand what these numbers are. They're just doing mathematical operations on that, and then it's trying to do the loss minimization as best as possible. And through that loss minimization, you're able to recover this, but it has no true understanding of what numbers are. I think it should be clear to most of you, but I think I hear in the internet all the time, like how smart these things are, but they are. An example I can give you is that if you put this sticker here on 3, so that it is somewhere between a 3 and an 8, a neural network is more likely to classify this as 8, whereas no human will make that mistake. So if you are driving on the street, you have other experiences to rely on. Through your lifetime of experiences, you know that no street will have a speed limit of 85. You know something is wrong. But a neural network, unless you account for all that, is going to happily fail and think that it is 85. So it's clever, but also easy to fool. That's a great time to take a break and ask some questions. So somebody asked, is Autoencoder basically doing the same thing as a principal component analysis? So mathematically, it's different. The PCA is another way of reducing dimensions and then squashing information into the principal axis. It achieves a similar purpose, but it's more general. So another question is, does the output of the encoder takes less space than the original input? Yes, definitely. So we compressed it down, right? So remember, each image is 28 by 28 or 784 parameters. And at the center of the encoder, we had only 32 nodes. So we have reduced it down from such a large input to a very small number of things. So that's the whole idea. The compression, doing compression is the whole idea behind the encoder. Another question about, can you show how to visualize print the latent space for an input? I will go over that later in the class. So there's no easy way. It's all time consuming, but I'll show you in a way you can approximate it. You cannot fully visualize it. So because it's in a higher dimension, it's like human beings it's very hard to visualize more than 3 dimensions, maybe 4 if you add time to the 3 dimensions. Beyond that, we can't really visualize it. So it's a big problem, right? Because most of these things can go into hundreds of dimensions, and how do we visualize these latent spaces? So there are ways to kind of even compress the latent space further, and then take stuff out and kind of visualize them as 3D graphs. They are time consuming, but they can be done. And I'll show you some examples of that. We won't go over how to do that exactly. You can look it up, something called the TSNE. I'll mention that. I'll give you the link also where you can go do that. Okay, so let's move on. So we have about 20 minutes left. Still a lot of material to cover, but let's see if we can get through it quickly. So the idea behind denoising was that you have a noisy image, and then you have some similar image and a clean image. So think of this as a distribution, right, of the same image. So there may be on one end of the spectrum is almost noise, like there is no discernible information there. On the other end of the spectrum is your pristine, clean image. And somewhere in between is like little noisy, and somewhere on this side is very clean, but not the final version. So again, it's hard to visualize it, but you can think of it as conceptually only, not mathematically, but that these images kind of form a distribution, right? They go from one extreme to the other, and in the peak is the average or something that you can get as a mean. So our goal is in denoising is to find an image from this distribution that is as close to the clean image. So, and that's like the essence of essentially all machine learning, is that we're always trying to find a distribution that matches the distribution that data came from, because we don't know where the data came from or how it came about. We know it came from some distribution. What we're trying to do is approximate that distribution. And the easiest way to approximate it is approximating it as a normal or a Gaussian distribution, because we know more about the Gaussian distribution. If we can say that this Gaussian distribution is close enough to the distribution that the data came from, then we can sample from the normal distribution, and then we'll get an image that is pretty close. So if you have a set of noisy images and a set of corresponding clean images, we can train our network to recover those images. You feed in the images, and you use the clean image as the ground truth, noisy as the input, and then loss function as the difference between the two. Train it enough, and then you can start feeding it images it has not seen before, and now you can start denoising the images, right? So many times we don't have the noisy image, right? So ray tracing is a particular example where it's easy to get noisy image because that's how the ray tracing algorithm works. But in general, if you have photograph, you don't know where to get the noisy version. How am I going to train it? So one thing we can try here is we can add noise to an image. So this part where you are taking data and modifying it, splicing it, turning it around, all this is like almost another field of data augmentation, where you can generate data that is non-existent in real life, but you're able to generate it. In fact, there are now all these efforts to build the metaverse, if you were, of reality, where you can take whole factory floors and model them and as detailed as possible, so it represents a real factory floor. So you can then try out your robots or other things in that virtual environment, and it would be how you generate data to train it. So you train those robots in that factory environment without having to spend all this amount creating a real factory or creating real robots. So you get pretty good mileage out of this. So this synthetic data field is going to grow as because it's cheaper to do it that way than to create real objects. So let me introduce now something called a convolutional neural network. So the main idea behind the convolutional neural network, or the way we use it, is to be able to reduce the number of nodes we have. So again, as I said, like any fully connected network will work fine. It will train whatever you want. The CNN has much fewer nodes, to almost a order of magnitude lower than a fully connected network. So that's one advantage. Second advantage is more perceptual. So it works in a way that is similar to the human eye, where you glance at objects, you get this initial idea of what these things are, first as like very gross texture, and then you start identifying lines at first, and then circles, and then at a higher level there are other features. The lines become boxes, and then the circles become objects. So that's the kind of way the human vision is arranged as well. And we're going to use a similar mechanism for that to make something called a CNN. It's called the convolutional neural network. If you have if you come from image processing world, a convolution filter is something very common. People do it all the time. If you, for edge detection or for embossing, if you have run these Photoshop filters ever, you should know that they basically use a convolution filter operation. Not necessarily a neural network, but a convolutional filter operator. So all that does is takes a subset of pixels, say 4 by 4, and it runs some operations on those pixels, and then replaces those 4 by 4 pixels by this one single pixel. So essentially, you've reduced the size of the image and replaced it by the average of 4 pixels, or average of 16 pixels. And then you do this operation, you move a little to the right, do the same operation, convolve again, do that again, do that again. Once you've gone through the entire image, you would have ended up with something called a feature map, which essentially takes in all these salient features of this image and makes it a smaller image, but all these features are present there. So when you average things, you get kind of a blurry version of these things, but you don't have to average. You can do any operation in this convolution filter. So there are specific operations for doing edge detection or embossing. In general, for convolutional neural network, you use an averaging function. So the upshot of this is that you reduce the number of nodes, because as you keep doing this further and further, you need fewer and fewer nodes in your network, and it becomes like a little bit faster to calculate than a fully connected network. At the cost of now you're doing more operations, right? A fully connected network, all it does is multiplies the weights, sums it up, and runs a activation function, where this is now doing convolution every 16 pixels and moving around the image. So it's doing more work, but overall it uses less memory. So once you do that, I think now you've extracted all the features out at a higher and higher level. First, you do the 16 pixels, and then you kind of do it more in a cascade, where you take that feature and run another convolution, and then it becomes smaller. So as you do this, you can also see the depth of this is increasing. So essentially, you are stacking all these features back to back. So you start with a image with 3 dimensions for color, and then as you make features, you have a smaller size but more depth, and then as you go one more convolution, you have even smaller size but even longer depth, and at some point you will end up with the result where then you can scale it back. So you can feed this to recognizing these features for what they are by labeling them. So this is how you can do object detection. You can even use this for the denoising that we used earlier. So it's a pretty handy network, and it's been used for the longest time now in the last few years to do all kinds of things. People have pre-trained all kinds of image data on this. So one of the best networks to use for all kinds of image operations. So we have a question about like the layers that after the convolution operation, what you get. It's called a feature map, and what you would like a heat map would be like, you can call it that, but it's not a heat map. It's not showing you, but it's gonna identify features where you have lines and dots, for example. And then as you go higher level, you start seeing more of like, finally, the eye is represented by one feature, or the hand is represented by another feature at the other extreme. So it starts from the kind of coarse to finer level of detail. Again, very similar to how the human eye works. So this is what it looks like. Essentially, the operation. It's a little bit misleading because it's in 3 dimensions, or in depth is the depth of the layer. So all the pixels behind them, they are also being averaged at the same time. Okay, so let's use CNN. And we'll use a little bit larger images, but we need some more machinery. So let's look at this denoiser.cnn, or denoiser.cnn.ipyn. And so there is some trick to kind of figuring out the node sizes and how to do convolution. I'll point you to this particular, I'll send out this slide as well. There's this paper which kind of describes the arithmetic of what exactly is happening, how to find these sizes. In practice, you don't need to, but if you are curious, you can find out more about like how exactly the math behind this works. Okay, so things are going to get complicated in terms of number of things we're doing in this particular sheet. There are going to be a lot of new concepts, but I'll explain to them. Let's see if we can cover this in the next 10 minutes. So we're going to go a little bit higher level. We're going to use something called TensorFlow dataset, and TensorFlow dataset has a lot of operations. The reason we're using it is because now we're using larger images, and we're going to be using 256 by 256. Imagine we were using 28 by 28. So this is 256 times 256 times 3. The networks will be large, data will be a whole lot. So first thing we do is load all of our things, and this is the data. It's called Merced, and we'll download it and prepare. Again, this will take some time. So I've preloaded that. You can try it after the lecture to see if it works for you. It should. So we're going to see what this data is. It's essentially satellite data. Satellite data, there's 256 by 256 pixels each. There is some training set as well. And it's also, there are some names for the classes also, like what this particular data is for. So this is just for something to show you the example of what this data looks like. There's just satellite images from different places. And it has some labels like overpass or tennis court or a freeway. So you can use it for classification, but we're going to use it for denoising. So because this is fairly large for a neural network, we are, instead of training the entire image size, we are going to train a small patch of it. So we're going to take all of this, like say this particular image of a freeway, we're going to chop it up into 128 by 128 boxes. So you get 4 boxes out of each image. That also augments our data in a way, because it gives us more data to work with. Because our goal is to denoise, so the denoising in different environments, it should work the same whether we use the full image or we use sections of it. So we can do that. Define this patch width and patch height. So, and I'm going to come back to these two functions in a minute. So let me talk a little bit about what we are doing here in terms of the data itself. So we're going to train, we have the training data and the testing data. So we're going to split it 70-30. We just found out the size of it is, and so this TensorFlow data set has its own method. They're different from pandas. So I'm using those called take. It will take 70% of the data and it will leave, skip and the rest, and then that will assign it to the testing. And this particular function called flatMap is going to bring all this data in, and we are asking it to run a function on it called extract patches. So this particular flatMap is like a map function in Python. It allows you to essentially run a function on a set of arguments. So in this case, the arguments are each of those images, and the function that we're going to run is extract patches. So now let's look at that extract patches. So extract patches, what we're going to do here is call this extract patches from TensorFlow image utility. We're going to define the size of our patch, which is this, where it starts, where it ends, so number of patches, and the strides, it's like how much to move. So we can also, using the same function, we can create overlapping patches, which is also totally fine. But in this case, we are taking one patch, which is 128 by 128, moving 128 in this direction. And so you get 4 exact different patches. So that's what strides define, is like how much to move before taking the next patch in the X dimension and the Y dimension. And then there's some other arguments that are not meaningful to this particular exercise, but this is what extract patches will do. So we're going to take this extract patch and then reformulate it into an image with the depth of 3, which is the RGB components of the image, and they're going to convert that into a data set from the tensor. And so that this is being run for each image that comes in. This is what flatMap does. So now that we have taken all the images that came in, basically augmented our data 4 folds by creating 4 patches out of each of those. Now we're going to add noise to each of those patches. So the way to add noise is we will generate a random noise with some given standard deviation. And that noise, we're going to add it to the patch. And then anything that goes above 1, we're going to clip it. And now we're going to return 2 sub-images. One is the noisy part and the original image that was not noisy. So essentially, for each of the patch, we are going to return 2 images. So both these functions can accomplish all of that. And let's take a look at what that might look like. I need to compile program. So I might have to download this data source again. So we'll finish it up next time. So, but take a look at this file and go through that. So, because this may take some time to download. It's a large amount of data, about 300 megabytes. So let's stop here. I think this is a good time to stop. And if you have, again, any questions, just to go over that, so this will basically create noisy patches. That this is the original. The one above that is the noisy version that we just added noise to, and same thing. So now we have our data ready for training. All right, so let's meet again on Monday. And thank you, everyone. If you have any questions, again, please don't hesitate to either connect with me on Twitter All right.